Welcome everybody to this keynote talk for our conference Popularizing STEM, Science and Technology in the 21st Century US Popular Culture. And I'm particularly glad to have Charles Adler for it, as we thought that the perspective of a scientist was going to be fundamental to complete and enrich our program. Charles is professor of physics at St. Mary's College, Maryland, where he has been a member of the physics faculty for the past 23 years. He received his doctorate in laser physics from Brown University in 1992. And he's the author of over 40 scientific papers and the popular book, Wizards, Aliens, and Starships, Physics and Math in Fantasy and Science Fiction. And the book won several awards, including 2015 Science Communication Award of the American Institute of Physics. And his great courses lecture series, How Science Shapes Science Fiction, was recently released by the Teaching Company. The title of his talk is The Importance of Storytelling, a Scientist's Perspective. And Charles, the floor is yours.
Thank you so much. Let me share the screen with you. Can everyone see that right now? All righty. Again, let me know also if you have any problems hearing me. I would like to thank everyone for inviting me to give this keynote talk here. It is a huge honor to be invited here. The theme of the conference is very dear to my heart, the idea of the sciences and humanities. What's that?
No, sorry, someone was unmuted.
Okay, sorry about that. The theme of the conference is very dear to my heart, the idea of the sciences and humanities seeking common ground. I can, again, if you see here the illustration here, one of my great heroes, Galileo Galilei, front piece from his book, Dialogues Concerning the Two Great World Systems, which we'll return to later on in the talk, is kind of an illustration of this idea of the commonality of the sciences and humanities, and that Galileo is not only a great scientist, but also a great writer as well. And so what I'd like to talk to you about today is the idea of storytelling in writing science. If you look at one of the, I think, if I looked at the inspirations for this conference, one of the inspirations seemed to be C.P. Snow's essay, The Two Cultures. And of course, his essay was, to a certain extent, about how many people in the humanities did not, in fact, understand the sciences very well. But I think that nowadays also it kind of cuts both ways, because many people in the sciences, or at least there is a stereotype that a lot of people in the sciences are also not that interested in the humanities either. And I do think that's a shame, because I think, in fact, the sciences can learn a lot from the humanities, particularly when we consider the art of writing, or even more particularly the art of storytelling. My theme today in this talk is this idea that the same ideas that go into good storytelling also go into good science writing as well. What's going on here? So, let me tell you a story. This is a friend of a friend story, I should say. It's actually about 30 years old at this point. But I have a friend, Charles Sukanik, who is currently the chair of the physics department at Old Dominion University. But this is when he was back as an introductory graduate student in the physics department at an Ivy League university. Let's call it Yale. And he was at a mixer where all the graduate students were invited to meet their professors on like the day before classes started. And one of the other students whom he was talking with went up to a professor and asked the professor, why was it that I was invited to Yale? Because I don't have particularly good, record in physics compared to some of the other people here. My mathematics isn't that great. And the physics professor actually gave him a very interesting response, which was that he said that basically the best predictor of success in graduate school at Yale University, at least in the Department of Physics, was not the students' skills in physics or mathematics, as measured by the GRE exam, the graduate record exams, which is an exam that I think, I'm not sure it's still being done, but at the time was basically taken by essentially anyone interested in going into graduate school, certainly in the sciences and particularly in physics. There was, it's somewhat like the SAT. There's a math section to it and a verbal section to it and things like that. And the professor said that the main predictor, at least for native English speakers who are applying to Yale, the main predictor of success in the physics department was not their score on the math portion of the exam or on the separate physics exam, but was in fact their score on the English, the verbal portion of the exam. And so this was actually a better predictor of success in the, in their graduate program than anything else was for students coming into the program. And so there's an interesting question: why was this? Why is this true? There are probably a lot of different issues. And again, he was talking mainly about people who were coming into the program whose native language was English. So this was not really correlated with their fluency in English. But I think the idea was that in some ways, skill in reading and writing was actually more important than their skill in physics, or perhaps was correlated in some ways with their skills as demonstrated in physics. I want to explore this idea a little bit. There's a stereotype that scientists, and particularly physicists, are kind of as popularized by media like, the TV show The Big Bang Theory and things like that, that we're culturally ignorant. We don't care about writing or literature. We kind of also arrogantly assume that we know better than anyone else about physics. We don't really care to teach people what we do. But the reality, I think, is a little bit different. I've known my share of arrogant and uncaring people in the sciences and elsewhere, but again, arrogant and uncaring people don't seem to be a lot more prevalent in the sciences than anywhere else. And in fact, most scientists are quite excited about what we do. We want to make sure, in fact, that everyone understands what we're doing and how excited we are about that. And we also kind of get disappointed when people don't understand or share our enthusiasm. To give you an example of this, I want to talk to you a little bit about my first cousin, Lynn Adler. She's the smart one in the family. She is a professor of biology at University of Massachusetts at Amherst, and she is an entomologist, or actually she's really an ecologist, but who studies the interactions of insects with plants. And she's so excited about her work that she started writing a children's book about it called The Princess of Bugs. And with her permission, I'm going to quote a few lines from it, just to show you this issue about how excited she is of her work and how much she likes communicating about it. Princess Melissa loved sparkly things like colorful ball gowns and glittering rings, but she'd dig in the dirt or climb high in a tree to search for a beautiful beetle or bee. She heard someone screaming, "Oh, help, it's a bee!" Melissa rushed over. "Hold still and let's see. It's yellow and black and it's buzzing." "That's true. But instead of 4 wings, you can see only 2. This creature is wearing a clever disguise. But insects that only have 2 wings are flies." And I think that demonstrates, again, her excited about her work and wants to share it with basically as many people as can be. If anyone actually is interested in publishing this, I give her contact information at the bottom there. But the issue here is that, kind of my premise here is that this excitement that she feels about science in this really wonderfully written book, well, I think a lot of the things that make good science, good writing in science, are things that basically are good in all forms of writing, but perhaps modified a little bit for the specific issues of science. Now, I'm not going to lay down any rules about this. The novelist Elmore Leonard wrote down 10 rules for writing. And my feeling about them, of course, they weren't really rules for writing. They were more rules for making people write more like Elmore Leonard. But I do want to explore some of the common things that make me enjoy reading a scientific paper and make me think that, in fact, a scientific paper is good or interesting. And one of the things I'm going to say here is I'm also going to use actually scientific papers, not popular writings about science like my book was, but in fact, real, basically scientific papers written for a scientific audience rather than for a general audience. But again, I think that the rules for writing are a bit similar. Now, the first thing actually I'm going to say is I'm going to break my rule a little bit here, but let me propose some guidelines about good science writing. All right. The first guideline I'm going to give is actually more of a personal issue, and it's actually more on the lines of a don't rather than a do. But it comes from many, many years of being a science professor. And it may seem a little bit funny to you, but there's a point behind it. First of all, don't measure anything. And let me tell you what I mean by this. As a professor of science, I am I do a lot of instructing in the labs. And as part of that, students have to write up lab reports. And lab reports basically are things that are like, in some ways, mini scientific papers. And my takeaway from 24 years of teaching these things is that we really don't teach our students how to write these things very, very well. So let me illustrate that. Okay, let me take a piece of literature. All right. Opening lines of a fairly famous book. In a hole in the ground, there lived a hobbit. Not a nasty, dirty, wet hole filled with the ends of worms and an oozy smell, nor yet a dry, bare, sandy hole with nothing in it to sit down on or to eat. It was a hobbit hole, and that means comfort. Of course, the opening lines of The Hobbit by J.R.R. Tolkien. But what I want to illustrate for you, and I did this exercise a while ago for some of my students, what would happen if a student took this and rewrote it as a lab exercise based on, again, my 24 years of reading student writing exercises here in terms of lab reports. So if we rewrote this as a lab report, how would it go? It would, as a typical student lab report. In this paper, we examined a hole in the ground. We measured the diameter of the hole. It was 2.5 plus or minus 0.3 meters. We measured the amount of sand in the hole. It was 0.7 plus 0.05 kilograms. We measured the number of worms in the hole. It was 3 plus or minus 1. From this, we determined the comfort of the hole using the formula blah, blah, blah. We calculated that the comfort was 1.2 plus or minus 0.4 meters divided by kilogram worms, or something like that. And I know this is being really kind of unfair to my students a little bit, but when you read through dozens of these things and start seeing things like this over and over again, it does start to get to you. And again, keeping in the same spirit of unfairness to my students, I will just simply quote a whole bunch of lines from their lab reports here. So here, opening of a sentence from student lab write-ups. We took readings on such and such a thing. We measured. We used a caliper to measure the diameter of a penny or something like that. We measured the voltage coming through a circuit. We calculated the resistance of this resistor. We propagated the error. We measured. We measured. We measured. And measured and measured and measured and measured. Measure is a weasel word. It doesn't really mean anything. Yes, we're we're in science. Of course, we are measuring things. And this, again, may seem like a pet gripe to everyone here and kind of a petty thing to be complaining about. But what it really is an issue of is the idea that students are not really thinking about what they are writing about. Again, when you say we measured, it is such a broad term and covers so many different things that is, in fact, the equivalent of being cliched here. Measurement doesn't really mean anything. So, and I try to impress this on the students, is that when they're in fact doing a lab write-up, they should treat it basically as any other writing exercise. They should think about the people that they are writing to, and they should actually, again, try to make it interesting by using a variety of different words, and also being somewhat more explicit about what they're doing, and also, in a sense, being more generous to their readers, which is the second thing that I want to talk about. Second thing I want to talk about in terms of good science writing is the issue of the generosity on part of the writer. So in contrast to those student lab write-ups, let me share you some actual sentences from a journal called the American Journal of Physics, sentences from papers published in that journal. Now, the American Journal of Physics is it's a journal which is not meant for original research. It's actually mainly meant for pedagogy, for physicists who are interested in teaching things in somewhat different ways, who have ideas for presenting material in different ways. There's a lot of stuff there's nothing really that's new or incredibly brilliant. There's nothing that really that's new or on the borders of research that's being published in this journal. What it is mainly for is people who have different ideas about how to present it. And so the writing standard is actually pretty good. It's meant mainly for instructors of physics, either professors or teachers, or graduate students or undergraduate students who are interested in teaching in physics. But again, if I quote from some lines in there, it does show you again the contrast between people who are writing here and the typical output that the students are giving us. So actual sentences from here. In this paper, we introduce the nonlinear effects on a pendulum to which a nonlinear periodic driving force is applied. We reveal that the mysterious amplitude quantization, initially studied as macroscopic quantum behavior, is in fact a subharmonic resonance. This problem aroused extensive interest among undergraduates and even high school students. So look how generous these people are being. They are introducing things to other people. They are revealing mysteries. They are arousing interest. They are being very generous with what they are giving, with what they are giving to their readers. They are making sure, and again, this is a serious point, even if I am trying to make it, a bit humorous here, is that what they are generously extending is the idea that they are fascinated by the things they are writing about and that the readers should be too. And again, this is one thing that I kind of took away from when I was writing my book as well, and also whenever writing a scientific paper, is that if I am not interested in what I am writing, and this happens more often, if I'm not interested in what I am writing, my general assumption is going to be that no one else is going to be interested about what I'm writing. And so I need to make it very plain that I am absolutely fascinated by what I am writing about, and that this needs to be made crystal clear to any reader that is reading my paper or reading a book. This sense of clarity goes into the next point, of course. So don't measure anything, be generous, be clear. And again, there's this kind of stereotype that scientific papers have to be mysterious or, phrased, somehow cloaked in jargon or filled with these weird equations that, are completely above and beyond what any quote unquote normal person can understand. But in point of fact, I think the best scientific papers are marked by a real sense of clarity, that in fact, the authors of the papers are striving to make things as clear as possible to their readers. To give you an example of that, I'm going to take a very famous paper on the electrodynamics of moving bodies by Albert Einstein. Now, I am going to quote from the translation that I have of it into English. I do not read German, unfortunately, so I can't quote the original German that it was written in. This is one of his papers from the miracle year of 1905. This is the first paper that he wrote about relativity. And in this, he is talking about some some things which I think most of his readers would have found very difficult to accept. The idea, for example, that measurement of times, there I use the word measurement, but the measurement of times and distances in different reference frames, or basically for people who are moving with respect to one another are going to be different. It's a very, very counterintuitive idea back then, and in fact, so counterintuitive that a lot of people don't actually accept it today. Well, let me quote from his paper, from some of the introductory sentences of his paper. Determinations of time are always judgments on simultaneous events. For example, we say that a train arrives here at 7 o'clock. This means that the exact pointing of the little hand of my watch to 7 and the arrival of the train are simultaneous events. So what he is doing here is defining what the time that an event happens at means. He is saying the train arrives at 7 o'clock means that as the train passes by where I am standing and I glance down at my watch reads 7. He had to do this because no one before him had actually really thought about what that meant. Everyone had kind of blithely assumed that if it was 7 o'clock on your watch, then it would still be 7 o'clock on the conductor's watch as he whizzed past you in the station, and that the two watches, if they were synchronized at that point, would still remain synchronized as the train moved through the station. But he goes on to say, after this, again, this issue of clarity here, but the definition is not sufficient when it is required to chronologically connect a series of events taking place at different places. That is, this synchronization, the fact that my watch reads 7 and the conductor's watch reads 7 when the train passes me in the station, does not mean that they will still remain synchronized. Now, the paper itself is somewhat mathematical, but he does, again, if you were, it is meant for other physicists, but again, even as a physicist, one can recognize, as a physicist, if you read through the paper, one recognizes just how logical the paper is, how everything stems from these first definitions and from his first postulates about the theory, about his relativity theory. These two postulates being that basically the laws of physics look the same, both to the person in the station and to the conductor on the train, but also that the speed of light, as measured both by the person standing in the station and as measured on the moving train, is going to have the same value, that the speed of light is constant no matter who is measuring it, no matter what state of motion they are in. One thing I also want to mention as well is that I read a fascinating paper once about this issue of clock synchronization that Einstein brings into here, which is that at the time that Einstein was writing, this was just a few years after, at least in Germany, when railroads had actually started synchronizing clocks between stations using electrical impulses. And at the time, engineers at the time had to actually consider the amount of time that it took for an electrical synchronization signal to go from one station to the other to correct the timing on the clocks. And this is quite possibly one of the things that led Einstein to his ideas behind the theory of relativity, but also certainly to this metaphor that he's using in here about, about this issue of what it means to synchronize two events. So this is, so again, reading Einstein's papers, certainly his original papers from 1905, to me, always feels like either like drinking from a cold, clear mountain stream, because the clarity of it is so great and such, and they make such logical sense, or like reading a very tightly plotted detective novel, because everything follows, just everything one on the next, on the next, on the next. This is something I may allude to later on, which is that different writers in science have very, very different styles. Einstein's style, it seems to me, was that, again, of this really inexorable logical, this inexorable logic that follows through his papers. Certainly his papers written in the Anno Mirabilis of 1905. Okay, so we have covered the issues of measuring things and generosity, and now clarity. the next thing I would like to consider is the issue of humor in these papers. I will say that humor is probably one of the toughest things to get past an editor if you're submitting a scientific paper to that. Stephen Hawking once made the complaint that whenever he was writing a paper about black holes, he would always try to insert a line in there like, a Martian watching someone fall into a black hole, or if people from if a UFO traveling nearly the speed of light went past a black hole, or something like that, lines like that. He complained that the editors would always take them out of his scientific papers before they were actually get published. So the humor that typically makes it past the reviewers in scientific papers, and possibly in other disciplines as well, I don't really know, tends to be more of the sort of sly, self-deprecating humor than any other kind. And let's talk a little bit about that as well, though. Okay. So my first example is from a paper called A Schematic Model of Baryons and Mesons by the physicist Murray Gell-Mann. This is the paper that introduced the concept of quarks. And, quarks are particles which make up protons and neutrons. And he's talking about how the idea of quarks as real particles, or as particles at least, fell into this issue of certain symmetries that existed among different elementary particles, protons, neutrons, other particles which are called baryons, which possessed a certain symmetries in relationship to each other, which other particles called leptons, electrons, tau particles, muons, things like that, did not possess. And so he basically had this idea of these hypothetical particles called quarks, but they were unlike other particles like electrons or protons, in that electron has a charge of, we'll call it -1, proton has a charge of +1, and in all elementary particles, all charges come in multiples of either -1 or +1, or sometimes 0. But you don't see things like -1/3 or +1/3 or -2/3. But he had these particles called quarks, which he had this idea had charges of +1/3 and -2/3. And so he wrote this paper about these quarks and about how these quarks would make up protons and neutrons in their almost elementary form, and other particles called mesons. Here you see examples of what's called a pi meson, a positively charged pi meson and a negatively charged pi meson, in which the proton is made up of 2 up quarks and a down quark. The neutron is made up of 2 down quarks and an up quark. The pi positive meson is an up quark and an anti-down quark, etc. But he had this to say at the very end of the paper, kind of, again, sly bit of self-deprecating humor there. It is fun to speculate about the way quarks would behave if they were physical particles of finite mass. A search for stable quarks would help to reassure us of the non-existence of real quarks. So, what he's saying here, he's basically being a little bit sly here. He's saying, well, yeah, as far as most other people are concerned, these really couldn't exist because charges only come in plus or minus 1. But, maybe we should look for them just in case we will reassure ourselves that they don't in fact exist. The other, and of course, one of the things about quarks, which was discovered later on, is that they in fact, they are, I don't know how people define reality, but they are real particles, and at least as much physicists think of particles as in terms of what physicists view as reality. They cannot, however, exist on their own for various reasons, which were later elucidated, I think, in the 1980s and 1990s. Second example comes from outside the field of physics, which comes from the seminal paper by James Watson and Francis Crick, a study for a structure for deoxyribose nucleic acid. This is the famous paper in Nature in which they showed, in fact, the structure of DNA in 1951, I believe. And of course, as most people understand the structure of DNA is basically that of a double helix with essentially base pairs attached in a complementary way. C is attached to G's, A is attached to adenine, attached to thymine, cytosine attached to, and I'm blanking on what the G stands for right now. Someone will probably remind me in a second. But again, the idea that these are complementary strands, that basically C is attached to G's, T is attached to A's, and so on. But the strand can be made of basically any arrangement of these. And so in fact, the genetic code, the coding of this structure, can be basically any arrangement of these that they want. And the very final sentence in the paper is, again, an example of kind of sly humor. It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for genetic material. That is to say, splitting the strands apart allows you to form a complementary strand by pairing up these opposites with each other. So again, an example, I think, of relatively sly humor, but again, a kind of a sly, almost self-deprecating humor in there, in that, yeah, they were very, very excited by realizing, in fact, again, that this structure showed, in fact, how DNA replicates itself or can be used to replicate itself, but they were deliberately playing it much more low key than that. Okay. So we now have the guidelines. Don't measure things, be generous, be clear, be humorous. Fifth point, use metaphor. So the next example I'm going to take about the issue of metaphor in scientific writing. And again, this kind of goes against what most people, I think, stereotypically think about scientific writing, in that it tends to be jargon-filled and equation-filled and things like that. And there are many papers that are like that. But the example I'm going to take right now is from the Theory of Positrons by the great physicist Richard Feynman. Feynman, of course, is well known as a popular science writer. His books, surely you're joking, Mr. Feynman, and blanking on the second book. He's also, of course, very famous for the Feynman Lectures on Physics, which are a set of introductory physics textbooks written from when he taught the introductory freshman classes at Caltech back in the 1960s. The Theory of Positrons was one of his first papers on quantum electrodynamics. Basically, the theory, what happens when you merge the theory of quantum mechanics with the theory of relativity. And the Theory of Positrons is, again, about positrons, anti-electrons, particles that are basically exactly like electrons, except that they have a positive charge instead of a negative charge, but exactly the same mass, exactly the same all other properties that an electron has. And this paper that he wrote was basically of his own view of quantum mechanics, the view of a theory called quantum electrodynamics that he was putting together, which was a very different view than two other physicists had put together at the time. Julian Schwinger, who had put together a far more algebraically based model for quantum electrodynamics. Again, this theory of relativity plus quantum mechanics. And Schwinger's theory involved a lot of manipulation of algebra-like terms on them, what are called operators. And another physicist in Japan, Tomonaga, had put together a very similar theory to Schwinger's. And both of these had these theories which they were using to predict various different things. Feynman's theory, on the other hand, was much more visually based. He had started doing these things that are now called Feynman diagrams. And he had this idea about what positrons really were, which was based to a certain extent on how his diagrams actually looked. So let me go through the metaphor, the key metaphor he used here. This is the very famous bombardier metaphor. A bombardier watching a single road through the bomb sight of a low-flying plane suddenly sees three roads, the confusion only resolving itself when two of them move together and disappear, and he realizes he has only passed over a long reverse switchback of a single road. So again, as you fly over the road, you see three roads, but they resolve themselves into a single road, basically going forward, back, and then forward again. The reversed section represents the positron in analogy, which is first created along with an electron and then moves about and annihilates another electron. Now, I'm not sharing kind of the key insight for the paper, which is more mathematical, but Feynman's conceptualization was that one could view a positron as an anti-electron as an electron which was moving backwards in time. What he realized was, in fact, that you could describe an anti-electron as basically an electron, but essentially an electron moving backwards in time would look like a positron, an anti-electron moving forward in time. And so if you look on here, you see these lines here. This is one of the first, I think, very primitive diagrams that he ever wrote, very similar to what eventually became called Feynman diagrams, is basically in point 1, an electron moving forward in time, annihilating with another positron moving forward in time. But on the right-hand side, you see line 2 going out. If you look at everything moving forward in time, the line 2 moving out is another electron, which was created by what is called pair creation, when a photon, a particle of light, scatters off of another particle. What he said was, well, no, you could view this in this following way. You could actually view this as an electron moving forward in time, but then turning into an anti-electron moving backwards in time, then turning into a regular electron and moving forwards in time again. It is as if a bombardier sees a switchback in a single road really looking like 3 roads instead of 1 road. And again, it's a beautiful analogy here. One of the other things about this analogy, of course, is that this paper, if you look at when this paper was written in 1948. The bombardier analogy apparently actually came from a graduate student at Cornell, which is where Feynman was teaching at the time, who had in fact been a bombardier in the Air Force during the Second World War. So again, the metaphor is actually directly traceable to the time and place when Feynman was writing this paper. So we have so far, don't measure, be generous, be clear, be humorous, use metaphor, and now invite a willing suspension of disbelief. And again, this willing suspension of disbelief is a term that comes mainly from science fiction. The idea that when one is reading a science fiction novel, you should be willing to suspend your disbelief about the weird things that are going on in the science fiction story that you're reading. The idea basically then that the faster than light travel exists, that aliens have landed and, want to take over the world, or, give us great, beautiful, wonderful technology, things like that, that someone can build a transporter to basically transport atoms from one place to another. Well, and the idea again being that you willingly suspend your disbelief to move into this sort of fantasy world that the author has created. I think that you wouldn't think that this should exist in science, where of course people are trying to get across the facts and these scientific theories. But in point of fact, I actually think that a willing suspension of disbelief really does exist, that scientists actually, when writing scientific papers, are really inviting this willing suspension of disbelief in their papers. Considering back to Einstein, for example, when Einstein was writing the relativity paper, essentially most people at the time believed in absolute space and absolute time. Watches, the readings on a watch didn't depend on one's state of motion. The length of a train did not depend on its speed moving down through the tunnel. So he was basically saying, well, if you accept these premises that I'm going to put forward, just believe them for the moment, suspend your disbelief in these premises, then everything else will follow because of that. Well, let me give you an example from a more modern paper, A Dynamical Approach to the Cosmological Constant by Shinji Mukayama and Lisa Randall. Lisa Randall is a very well-known professor at Harvard University. She's in the she's in the Department of Physics and Astrophysics there. She, in fact, proposed a model called, I am blanking on this, a model, basically an alternative to string theory for essentially unifying elementary particle physics. It's about a decade ago. And it's an interesting model. I don't believe that I do not know, since this is not my specific field, I don't know, in fact, how well this model is accepted, but people seem to treat it as an interesting model. And in fact, have spent a fair amount of time looking at it. In this paper, she starts with the sentence, "The cosmological constant remains the biggest puzzle plaguing particle physics. There is no known mechanism that guarantees zero or nearly zero energy in a stable or metastable minimum energy configuration." So I need to translate this a little bit, although again, if you're a physicist, you'll probably, you do understand kind of what she's going at. The idea here is that this cosmological constant is a term that Albert Einstein invented for his general theory of relativity, which he felt that he needed in order to keep the universe from collapsing back on itself due to the mutual gravitational interaction of everything in there. He abandoned this later on. It was a term that was consistent with his general theory of relativity, his theory of gravity, and it was kind of a term that more or less put together sort of almost an anti-gravity field existing throughout all of space that basically kept matter on its largest scale from collapsing back down. He abandoned this idea once Hubble discovered the fact that the universe was expanding outward from the Big Bang, essentially. And he really didn't need this term because the universe was not static. You need a term like that in order to keep the universe from collapsing in on itself if the universe were unmoving. But because the universe is expanding, you didn't need it. Back in 1998, however, a number of physicists actually discovered that there probably is a real cosmological constant term. The problem being is that this term is very, very, very small. It's called nowadays the vacuum energy, and it is a very, very tiny value, or very, very small value. And the problem is that theoretical physics essentially predicts values, if you go to the kind of the standard model of particle physics, predicts values that are either really, really, really unbelievably large, like a Google times as large as it ought to be, one followed by 100 zeros times as large as it ought to be, or identically zero. There doesn't seem to be a mechanism that seemingly makes it the small value that it is. Randall goes on to write, Randall and Mukayama go on to write, "It seems likely that the correct way to interpret the tiny value of the cosmological constant is that conventional quantum field theory is not the whole story, so it is worth seeking acceptable modifications." Here is your invitation to a willing suspension of disbelief. What they are writing is that let's, for a moment, just believe that conventional quantum theory isn't correct. If we vary that idea, what does it give us? And they're saying, just suspend your disbelief until the end of the paper. When we've tracked out this idea, if we explore this idea and show you that our ideas basically make this term really small, but not quite zero, the way it really is in the real universe. And so maybe this idea is in fact, is worthwhile considering. Okay, so these are the examples that I wanted to give today about what I consider good ideas for writing science, and in fact, what scientists can kind of take away from other types of writing. If we do try to kind of put these all together, what these all kind of have in common with each other are things that I think are common to other styles of writing as well, fiction writing as well. The idea, again, of keeping readers' interest in these stories, keeping them interested in the stories by basically making the stories clear, using metaphors, making them, not overusing certain words like measurement, using interesting vocabulary there, being generous with the audience. So keeping their interest, inviting a sense of drama, this issue of kind of, again, using the sly humor, the way that Watson and Crick did at the end of their story, saying, it has not escaped our notice that this suggests a method for, for copying genetic information. Even a sense of plot, this issue of Randall's paper where they, where they write that, again, if we suspend disbelief, let's work through these ideas and see that at the end we get this thing which is which is really worthwhile considering. So to end it all, I want to actually put all these sort of ideas together and talk about, again, one of my favorite science writers, whom I mentioned at the beginning of the talk, Galileo Galilei. He's one of my favorite science writers of all time. And his book, Dialogues Concerning the Two World Systems, is, in my opinion, one of the best written scientific books of all time as well. And again, I will apologize that I've only read it in translation, in that I do not read Italian. But I think this book actually combines many of these things that I've mentioned here all in one place. It's a long book, but it is very well worth reading, even if you are, and this is one, in fact, that can, in fact, be read by a non-scientist, even though it is meant actually for both non-scientists and scientists, and it is a bit dense going at times, but it is a wonderful book, and let me just mention a few features of it. I should also mention that the image of the painting I'm putting up is that of Galileo's famous meeting with John Milton, which I thought actually very appropriate for a conference like this one. So at the beginning of the book, after discussing why he's writing the book, he says, "To this end, I have taken the Copernican side in the discourse, proceeding as a pure mathematical hypothesis and striving by every artifice to show it superior to the Earth being motionless." So this book, the dialogue concerning the two chief world systems, Ptolemaic and Copernican, was Galileo's attempt to show, in fact, why the Copernican system of the universe was superior to that of the Ptolemaic system. Galileo, of course, was operating under constraint at the time, which was that he had been forbidden by the church to actually teach or hold that Copernicus's theories were true. So again, this issue of sly humor here basically is saying, well, I'm just going to take this as a mathematical position. I'm not actually going to say I believe in this. But he has a dialogue between three different people, or trialogue if you prefer. Simplicio, who stands in for the people who are arguing for the Ptolemaic viewpoint, the geocentric viewpoint, the Earth not moving. Salviati, who is a stand-in for himself, arguing the Copernican point of view, and Sagredo, who is basically supposedly a neutral observer. All these sides with Salviati all the time. What Galileo, this is a wonderful book because by doing this in the form of a discourse, he essentially can use all of the literary tropes, all of the literary devices that one can use. It's a very humorous book. It involves that, although it is highly dramatic in that the conversations get quite heated at times. It is written with absolute clarity. It is dense at places, but Galileo always explains his viewpoints. Salviati, I should say, through Galileo, explains his viewpoints with absolute clarity, and again demolishes Simplicio's argument. And of course, it was this demolishing of Simplicio's arguments that got Galileo into trouble in the first place. But I hold this up as a model for anyone who actually wants to do scientific writing, because it does in fact have in it all of those features that I mentioned. I thought were actually basically characteristic of good scientific writing. So that, I think, concludes what I wanted to say to everyone. The final thing I would like to say, of course, is thank you for having me at this conference. And I'm hoping that I neither went really badly over my time or under it, because I wasn't really paying that much attention to the time. But again, thank you so much for being at this talk. And I would be very happy to take any questions if people wanted to ask questions.
Thank you. I think it was very interesting, absolutely interesting. And what I mostly, while maybe the audience can come up with some questions for you, but what I found very interesting is that it absolutely resonates with what I feel should be writing in the humanities as well, because it seems that we are maybe assumed to write in a more entertaining and a more narrative way, but it's not true. There's so much bad writing in the humanities as well. And I think that your points were very interesting because, fascinating your readers, clarity, a little bit of humor, you know, that you can just let seep in, the use of metaphors well. And, you know, what you say that I really like is being generous with your readers. And it's quite, I see all this as opposed to what a lot of times happens, I think, in the humanities. There is this tendency to maybe impose yourself as an author, impose your epistemic authority, your jargon to show that you know what you're talking about. And I think this is, I don't know if it's a sign of insecurity, a sign that you need to show through your language and through making things convoluted and mysterious, that you know about your topic. But I think it's quite the opposite. I mean, if I really want to show people that I know about my topic, I show it by explaining it and engaging the reader and showing that I'm passionate about what I'm writing about, and build a little bit of suspense, as you say, at the beginning, just to create a little bit of a plot in a way, and the suspension of disbelief that I'm going to say, yes, you know, I'm trying to create a framework here, and just for a second, follow me on my journey. And at the end of the paper, you will see that I get to a point, and then you as a reader will judge if I got to a good point, a bad point, if the path was a good one or not. So I mean, I absolutely agree that good writing should be a little bit more, I don't know, is it about structure? Is it about, what do you think? Do you feel that in your field as well, there is a bit of this, I need to show off in a way that it makes it incomprehensible? And I don't know, because sometimes you're reading some papers, even humanities papers, and you have to read every phrase twice. Mm-hmm. And you get this feeling that you're being kind of set back. I don't know, like, I don't know enough to understand mm-hmm. you, and that's not very engaging.
The some of it is structure, certainly, but a lot of it, I think, I will say one thing. I was being a little bit, I was cheating a little bit in that the papers that I pulled out are ones that are, in fact, in some sense, really important papers. Einstein's, yes, thank you, yeah, thank you for that. If you can't explain to a 6-year-old, you don't understand it yourself. Yes, and I feel that that's, in fact, very true. A lot. But I did pick out papers that are kind of important or seminal ones in their particular fields. And so with that idea in mind, because a lot of them were papers that were actually trying to introduce really new ideas into physics, I think there was a tendency in terms of that to sort of be a little bit more general than one might be. One of the problems, I think, is over-specialization. I've been reading a lot of papers recently, for example, about turbulence. And because of a project that I'm working on with some other collaborators involving propagation of light waves through water or air or things like that, that involves basically kind of, the blurring of the light wave because of that, and the problems with imaging through media that have turbulence in them. Many of those papers are really incomprehensible because of the amount of jargon that's used there, or at least very, very, very specialized terminology that no one outside of their field can understand. And a lot of these papers could be rewritten much better if they'd simply started with an introductory sentence saying, this is what we mean by such and such, or these are the problems that we're trying to face, rather than just diving immediately into it and saying, well, the Fried parameter is defined as blah blah blah. Yeah, it's not good. I don't know if that answered the question, but I think over-specialization and the unwillingness to sort of look out of your own sort of narrow subfield is a large part of the problem that people have when they're writing. Because again, in many ways, that's what they were taught when they were graduate students, for example. They didn't really look outside of this sort of very narrow specialization that they were in. And so they're writing papers that are going to be only readable by, a few other people. And again, they want to impress these three or four other people by how much they know about their own particular little subfield, to the point where it's almost incomprehensible for anyone outside of the field, and possibly even for people inside that field. So yeah, I would agree to a certain extent that is it. And structure also has a large part to do with it as well, is that if you kind of structure it in the sense of a story, it's going to be a lot more readable than you kind of throw in various different elements. Sometimes I feel that a lot of scientific writers don't bother outlining papers before they start writing them as well, which just one of those other sort of skills that you can get from the humanities.
Yeah, I guess so. And when it comes to maybe, as you were mentioning, students, when it comes to early career scholars, sometimes I think as well, there is this perception that you really have to show that you're good enough. And how you do that, just by showing that you know the jargon and you can write with a lot of it. And I don't know, it makes me feel sorry, because in reality, there could be so much fresh ideas and maybe original takes that get maybe channeled in this kind of way that gets lost. And we have a question.
Yes. What
by
role,
Emma.
Did you want to read this, or shall I? Or
it's the same, if you want to
okay.
read it out.
What role do you think journal editors should have in improving the quality of writing, and how could this be done efficiently as time is a challenge? I think the most efficient way to do this is to give it more time, but unfortunately that seems to be against much of what is common practice. Most journal editors, unfortunately, are not trained in this, at least in the sciences, are not really trained editing in the sense that editing is done in the humanities. What most journal editors will look for typically is scientific accuracy over writing style. And what that means, in fact, I'm not sure how this works in the humanities, but I've served as an editor for a couple of special issues of the journal Applied Optics, and time again being what it was, what would happen is that I would get sent a lot of papers on a particular topic, and then I would start having to play round robin, which is basically trying to find people who could possibly review these papers, send them out to them as quickly as possible, get the comments back, try to decide if these papers were worthy of publication. That is not a situation which lends itself to the evaluation of good writing. Yeah, exactly. Yes. And I imagine it's very much the same everywhere. Yeah, exactly. And this is not conducive to any sense of good writing, because you basically have a turnaround time of a few months. And so luckily, I was in the situation where, because of the field that I was working in, and the people in general tended to be much better writers than in science in general. There were exceptions, of course, but a lot of the time, what editors will simply do is try to mark up the most egregious examples. But generally speaking, what we're trying to judge papers on is more scientific correctness than written style. And if they're scientifically correct, then generally speaking, we're supposed to accept the papers for publication, or at least as far as we can tell. And I think you'd have to, number one, you would need a cultural change for this. Basically, editors essentially going around and saying, look, we need to add in, writing style, clarity, clarity, and things like that into the process in order to be able to judge this. There are certain journals that do this. I mentioned the American Journal of Physics. The American Journal of Physics actually does, I think, include the fact that these papers should be clearly written because of the purposes of the journal. And other journals do also pay this lip service, but a lot of the stuff that gets in is still pretty hard to understand. My experience is social.
Yeah, she says that social science writers are probably the worst for using jargon, perhaps Anna's point of insecure. Even getting them to follow journal instruction is sometimes problematic.
The very little experience I've had of this involved a talk that I gave as part of the lecture series that that Anna mentioned for the teaching company, where I gave a lecture on this is horrible. I'm blanking on the idea right now, but the idea that language shapes thought. There's a name for this. Somebody's hypothesis, and I'm just blanking on that. I do remember having to read a number of papers in the social sciences about this particular concept, and I'm going to kick myself when I remember the idea. It was based on the movie Arrival, the one where, in any event, I do remember them being fairly tough to go through, because the thing that I remembered, in fact, was different articles not even basically agreeing, different authors basically not even being able to agree on kind of the fundamental concept. Sapir-Whorf hypothesis, thank you. Yes, the Sapir-Whorf hypothesis. Thank you so much for finding that. And I don't know how seriously this is taken in the social sciences, but it was a good hook for the lecture. But the papers that I read about the Sapir-Whorf hypothesis, the authors really couldn't even agree on what it was fundamentally. I just expressed the general idea, but how deep it went in terms of language governing thought, different authors disagreed about that, and therefore disagreed on whether it was correct or not based on different interpretations of what it meant. I don't know if that is specific to the social sciences. Yes, yes, thank you. Yeah, the Sapir-Whorf. Yeah, thank you for finding that for me. And I can, yeah. But it's worse in my case because I delivered an entire lecture on it just a few months ago. So,
well, I think that is, if I have to think of how it works in the editorial area in the humanities, I think that unfortunately sometimes what happens it's the opposite. So some reviewers just, I don't know if because they don't have the time, but they picked up the peer review anyway. Mm-hmm. They don't have the time, the interest, or maybe they're not even that prepared on that topic, and they don't have the the will to just check a few things out. So sometimes they just concentrate on the language, and they're just telling you because they don't like the style. And it's often, it's quite maddening because sometimes it's really about personal taste, Of course, if it's too convoluted, you can point it out. But sometimes you really feel that they're just correcting stuff that it's not quite the point. And maybe other content stuff just goes by. And when you're the editor, maybe you're rereading the paper and you're like, how did the peer reviewer not notice that they were saying something wrong, openly wrong, or citing stuff wrongly, So I guess,
I've seen that. Yeah, letting form obscure content. Yeah, my talk was mostly about form rather than content. But yes, I have certainly seen that happen as well. And I've certainly seen papers that came out which seemed to be reasonably well written, but completely did seem to just be so wrong as far as their interpretation of the science or the fundamental science itself went. The only thing I can say is people are human, and it's a very being a reviewer is in many ways I think worse than actually a worse job than actually or is much tougher, I should say, than actually writing the paper itself.
Yeah, I think as well. The editorial work itself, it's sometimes, I don't know, there are good editors and bad editors, and some just don't really have I don't know if for lack of time or lack of interest sometimes as well, or maybe you formed yourself in an environment that didn't have very good editorial practice. So sometimes it's just, even the editor has a weight, and that weight is not always there. So it's just, I think that's the way it is. It's also a lot of work for free.
Right. Yes.
So.
And we tend to push it to the bottom of the list, unfortunately, when we get assigned the duties. I completely understand that as well. It's just, yeah. We do it because we feel we owe it to the community, to our communities, but it's a very, very difficult and thankless job. So
yeah, I think so.
yeah.
Anyway, I think if the public doesn't have any extra question, I think we could call it a day.
Thank you so much, everyone, for having me here.
Thanks to you. It was very interesting, and as I told you before, it was really kind of an extra that we needed in this conference, because we've been talking a lot about science fiction and so on, but the science part of it was maybe a bit missing still. So thank you very much. Thanks to the public that was with us. I'm going to